Hello everyone and welcome to my channel. In this video I will teach you how to plot phase portraits and state space trajectories of dynamical systems in MATLAB. In order to make the long story short, in this video you will learn how to plot a phase portrait of the system that looks like this, and the result is given over here. Look at this nice graph. I will teach you how to generate this graph in MATLAB. Those of you who are my subscribers or who follow my work know by now that I always create a post that nicely summarizes everything that I will explain in this video, and consequently here is the post. This post contains graphs, equations, and MATLAB codes. A link to this post is given in the description below. Before I start, I would like to mention the following. It took me a significant amount of time, energy, and planning to create this post and this video. Consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. Okay, so let's start. Phase portraits are used to visualize state space trajectories of dynamical systems. And if you're not familiar with phase portraits, my advice is to open a book on dynamical systems or to, for example, read this Wikipedia page where you can find basic information about state space models, about state space trajectories, about phase portraits, and the nice thing is also that you have a few references here. A good reference on dynamical systems is this book over here. Here is a basic idea for drawing the phase portraits. We start from our dynamics. X dot is equal to f1 of x and f2 of x, where the vector x has two components, x1 and x2. Let this be our trajectory. Now the question is, what is a graphical interpretation of the vector x dot in the Cartesian coordinate system given over here, x1 and x2? Obviously, the vector x dot defines a tangent to our trajectory. That is, this is our vector x dot, and this vector has two projections. The first projection is f1, and the second projection is obviously f2. So knowing this and keeping in mind that x dot is tangent to our state space trajectories, we can follow the following strategy in order to construct the phase portrait. So what do? Let this be our coordinate system, x1 and x2. Then we discretize this space. That is, we define a grid. In MATLAB, as you will see later on, we can use the mesh grid function in order to define this grid. Then, at every grid point, we compute f1 and we compute f2. Basically, we compute the components f1 and the component f2 of our tangent vector x dot. We repeat this procedure for every grid point. most likely in every grid point we will obtain a different tangent. Here we should be careful since this is not x2, this is simply x dot. And this is the basic idea for constructing the phase portrait. Discretize the Euclidean space x1 and x2, define the grid, and in every grid compute the projections of this vector. These projections are f1 and f2, and they are defined by the right hand side of our state space model. And in the end, we will obtain a very dense grid of vectors that will define our phase portrait. For example, for the spiral, we will obtain something that looks like this. The first step is to write a MATLAB function that will define the system dynamics. That is, that will define our state space model. And here's the function. I call this function dynamics.m. This function defines the following state space model. x1 dot is equal to minus x1 minus 3x2 and x2 dot is equal to 3x1 minus x2. The function dynamics defining our state space model takes two arguments. The first argument is time, and the second argument is our state space vector. X is equal x1 and x2. This vector over here, dx, defines the right-hand side of our state space model. Of course, you can easily modify this function if you want to change the form of the dynamics. For example, you can see over here that I defined two other state space models. For example, here I have a state space model that looks like this. x1 dot is equal to x2 and x2 dot is equal to minus sinus of x1. The function dynamics returns the right-hand side of our state space model. That is, it returns x dot or dx. It's very important to save this function in a specific folder and to make sure that this folder is currently active. For example, over here you can see that the dynamics is saved in this folder and this folder is currently active. You can also save this function in another folder, however, then you need to add that folder to the MATLAB path. You can do that by, for example, clicking on Home, Set Path, and here you can find your folder and you can add this folder to the MATLAB path. I'm not going to do that in this example since I will make sure that my active folder is the correct folder. That is the folder in which the function dynamics is saved. Okay, so that was our dynamics. Here's our main file. First of all, we will define the limits of our phase portrait. We will define two vectors, x1 and x2, and these vectors will define the limits and they will also define the resolution of our phase portrait. You can see, for example, that x1 starts from -2, ends at 2, and we have 20 steps. Similarly, x2 starts from -2, ends at 2, and it has 20 steps. To summarize, the vector x1 defines the limit for the state variable x1, and the vector x2 defines the limit for the variable x2. And as you will see later, we will define a grid by using these vectors. And in every point of this grid, we will evaluate the right-hand side of our dynamics in order to sketch the phase portrait. The phase portrait is plotted by this function. It's called phase portrait, and we call this function from our main file. The first argument of this function is a function handle. Basically, it's the name of the function that defines the state space model or the dynamics. In our case, the name of the function is dynamics.m. Consequently, we write @dynamics as the first argument. Then we specify x1 and x2 vectors that define the limits of our phase portrait. Here's our phase portrait function. Here I will do one trick in order to better explain you this code. After function, I will type keyboard and I will save this function. So what will happen over here? Once I call my phase portrait from the main file, my code will stop over here. Keyboard command is a very useful tool for debugging the code and for explaining the code. So let's do that. Here I selected my code and I click on Evaluate section and see what happens over here. We are currently over here. We are at the code line 10, and from here I can manually execute other command lines. The first step is to define a grid. We define the grid by using the meshGrid function. We specify x1 and x2 vectors, and you can see them over here. This is another nice property of MATLAB debugger because you can immediately see all the variables. And let us define a meshGrid. The meshGrid function returns two matrices. It returns the matrix X and matrix Y, and these matrices basically define a grid. In order to make this video as short as possible, in this video I will not explain the meshGrid function. However, don't give up on this video because I created another video that explains the meshGrid function. So go on my website and over here type meshGrid and click on search. And here's the post and tutorial that explain the meshGrid function. My advice is to read this tutorial. A link to this tutorial will be provided in the description below. Okay, so let's go back to our MATLAB code. The next step is to define two vectors u and v that will store x1 dot and x2 dot. The vector u will store x1 dot defined for certain meshGrid points, and the vector v will store x2 dot. Next, we set time to 0 since our dynamics is time invariant, that is, our state space model does not depend on time, and here we extract the dimensions of our meshGrid. Then we define two for loops that will iterate over the meshGrid matrices x and y, and at every point of our meshGrid we will evaluate x1 dot and x2 dot. Let us graphically represent this piece of code. Over here we are taking points from our grid and we are evaluating the right-hand side of the state space model at certain points. These are the points, And these points have coordinates x, I, j, comma, y, I, j. This is basically our x1, and this is basically our x2. Then we take x1 and x2 and we evaluate the right-hand side of our dynamics. Notice over here that f is just a handle for the function that defines the dynamics. Our function that defines the dynamics is called dynamics.m. So instead of this f, when the code is being compiled and executed, we have dynamics. To summarize, what happens over here, we iterate over the grid points, that is, over the mesh grid matrices, and for every point we evaluate x dot, that is, we compute x1 dot, x2 dot. We basically specify if this is the first equation, x1, and we specify x2. Actually, we specify f2. So this is what we do. This function f returns the right-hand side of our dynamics. Then u will correspond to this part over here, and v corresponds to this part over here. That is, u is x1 dot and v is x2 dot. The variables u and v are very important since they define the tangent to our state space trajectory. Let us visualize the tangent, the trajectory, and these quantities. Let this be our state space trajectory. Next, let us sketch the grid. So here's our grid. Since the trajectory passes through this grid point, this point has these coordinates. The coordinates are given over here. They're x and y. Here's our tangent. Basically, this tangent is nothing less than our x dot. The projections onto the x and y axis of this tangent are basically our quantities u and v. So u is this projection. We can also say that u is a vector. This is u, and this is v. So, knowing the quantities u and v, we can basically construct a tangent to our state space trajectories at every grid point. For example, in this point, knowing that u and v are computed, we can construct a tangent to our trajectory. On the other hand, in this point, the tangent might look like this. And in this point over here, the tangent can look like this. So one of the possible trajectories can look, for example, like this. The trajectory can go like this. It should be tangent to this vector, then like this, and then like this. So that's the basic idea for constructing the phase portrait. At every grid point, we compute, or we better to say, approximate the tangent to to our trajectory. And the coordinates of these tangents are stored in the matrices U and V. Next, let us execute this piece of code. Okay, and now we are almost done. The next step is to use this MATLAB's function called quiver to plot the phase portrait. Let's do that. Voila! Here's our phase portrait. Let us erase this keyboard over here, save the file, and let us call the phase portrait function again from our main file in order to verify that everything works fine. Here it is, everything works fine, so we are able to generate our phase portrait. Next, let us discretize the dynamics, that is, let us solve our ordinary differential equation, or better to say, let us integrate our state space model, and let us plot the state space trajectory on the phase portrait. For that purpose, we need to define the discretization step. T defines the discretization step, then we select the total time for simulating the dynamics, and we choose the initial state. In this case, x1 is 2 and x2 is 0.5. Then I'm using the ODE 45 to solve my dynamics. To ODE 45, I specify the handle, the function handle that defines my dynamics. Here's my dynamics. I specify the time and I specify the initial state. After that, I plot the trajectory, I plot the initial state, I plot the final state, and I plot all the points in between the initial and the final state. So let us see the result. I will select everything and I will evaluate my code. So here is the result. This graph looks amazing in my opinion. We start from here, this is our initial state, and as you can see, we are moving along this spiral and we reach our end state that's given over here. And you can see also that our vectors defined by U and V are approximately tangent to our trajectory. Okay, that will be all for today. I hope that you like this video. If you like the videos I create, please subscribe, press the like button, or support my channel. Thank you very much and have a nice day.